well,
We'll take it to the Davis paintball.
we do plan on doing that inside the computer club. We do plan on doing a century. We were supposed to do one this semester.
Well, don't blame me when membership drops next year.
Going down there.
Oh, well, we're not going to shoot each other.
All right, so the recording is on. So what I'll do is I will basically give you your homework assignment first, and then we'll talk about the concepts that you need to understand to get the homework assignment done. This one is going to be, it's going to be a little bit more difficult than the one that you just turned in. The one that you just turned in is, you spend more time typing the tar command than actually doing the homework assignment. This one is a little bit different. Okay, so the homework assignment is about complex numbers. You don't really need to know complex numbers in math because everything is already defined in C. So what your job is really just to translate C code into assembly code. And you don't have to copy and paste any code because I made a tarball for you. So it makes everything easy. Well, sometimes when it's so easy to set up, then you have to ask, okay, why is it so easy to set up?
Because it's a trick.
No, there's no trick.
Yeah, it's a trap.
Okay, so we'll do a tar xcvf. It's in my downloads folders. It's called complex.tar.gz. So it will create its own folder with all the source file in it already. So if you go into complex, you will find a bunch of source files. So other than main.c, for the other two source files, you have to convert all the subroutines into assembly code. So let's take a quick look at what kind of code we are talking about here. First thing first, we will take a look at the header file. And this is the header file of complex, which is defining the structure called complex. Okay? It has two members. One is called I, one is called R. They are both 32-bit signed integers. So are there any questions about the structure itself from line 4 to line 7? It's a structure, it's a cookie cutter, and it has two members. One is I, one is R. I, by the way, stands for imaginary, and R stands for real, for those of you who already understand complex numbers in math. Are there any questions about this part? From the programming perspective, are there any questions? Okay. If there are no questions, we're going to switch to the C code. So we'll take a look at complex.c first. So Yep.
I'm only familiar with C++ classes. So in here, a struct doesn't need any kind of logic to learn how to turn that, like on line 10, particularly. Or line 10. So
I'm passing by value in this case.
So that you're passing. So since it, oh no, it doesn't have no constructor. So
there's no constructor in structure. This is plain C. It's not C++. So there are no constructors. You're just copying everything onto the stack.
Okay. So, but oh no, okay, those are functions. So
those are functions. Those are function prototypes. So from line 9 to line 12, those are all function prototypes, which tells the compiler how to compile the code when you're calling those subroutines. So when you go into complex.c, those are the actual definitions of the subroutines. So when you look at line 4 to line 11, for instance, that is how we add. This is how we initialize a complex number. And the trick is, we have a local variable called x, and it is getting initialized, and I return it. In other words, I'm returning an entire structure. Okay? It can be done. I will illustrate how it is done today. Okay? When you look at complex add, it's about the same, except it has got parameters that are also complex numbers. So when you are adding complex numbers, you're adding the I component separately, and then you're adding the R component separately, and that becomes the result. Are there any questions about the subroutines themselves? Okay, all right. And let's scroll down to the last one, the multiply one, okay, complex multiply. Are there any questions about the multiplication? It's just a little bit more complex than the add and the subtract, the add and initialize, because you have to multiply the I with the R and the R with the I to get the I. Okay, so when you multiply a real number with an imaginary number, you end up with an imaginary number. When you multiply the I component with the I component, you get -1. Okay, because the imaginary number is the square root of -1. So this is all math stuff. You don't have to really understand how it works or the math behind it. You just have to implement the logic so that your assembly code would do the same thing. Are there any questions about this part? No questions? All right. And then we have the another subroutine just to do the printf, so that you can print the R component and the I component using just a regular printf. When you call the printf subroutine, it's no different than calling any other subroutine. You push the parameters backwards, last parameter first, and then you call your printf. Yep. Oh, okay, great. So in other words, the convention of calling subroutines does not even change when you're calling subroutines from the C library. It's the same thing. You just have to push the parameters backwards and then call the subroutine itself. Are there any questions on this slide? Okay. Yep.
Which part is stay in C, which part we have to implement in use S?
You're going to translate everything you see here into assembly.
So for printer, we are printed in C, right?
No, you call printf. If the C code is calling printf to do the printing, you are going to call printf to do the printing.
It's in C or in assembly?
In assembly. So you'll be writing everything in assembly just to do the same thing that we are doing in C, in the C source code. Okay? But there's one more subroutine, okay? So there are a few here, and there's one more. That one more is in complex test.c, and it's called ABC, just because I could not find a good name for this particular subroutine, so it's just called ABC. It has 3 parameters. Each one is a complex structure. They're all passed by value. Okay, nothing is passed by reference or pointer in this case. They're all passed by value. And the complexity of this particular subroutine has to do with we are calling the other subroutine. In other words, not only do you have to understand how to intercept parameters that are complex structures, you also have to know how to call another subroutine that is doing this. Okay? So that's going to be, yep, go ahead.
I was just going to say, so basically the assignment is to flatten it into assembly.
You have to do everything into assembly by observing some of the standards, okay, some of the calling standards. Okay, so this is all the subroutines that you have to implement in assembly. But the biggest problem, is I can go in here and I can reverse I and R, and your program should still work. I can insert additional members, X, Y, Z, between I and R. Your code is still supposed to work. Is that okay so far? So the make file should be able to take care of everything, so that when I redefine the structure in C in the header file, your assembly code through the make file will respond to that change and update itself automatically and say, no problem, I can get to member I and member R because of some really interesting mechanism that we'll be talking about today.
Is that mechanism part of the make utility?
Eventually it will be rolled into the make file, so we'll be working on that today, using a sample program. Okay. Any other questions? Well, if there are no questions, we'll go ahead and start to do this. Okay. All right. And since I'm not going to work on your homework assignment, I have to find a new structure to play with. So I'm just going to play with.
You don't have to go to all that trouble. We'll understand.
Well, let's see. What am I going to do? Coordinates. Okay, so that would be a good one. All right. So what I'll do is I'm going to write the header file first. So when I'm writing the header file, what I'm really doing is I'm defining the structure itself. Okay, does everybody understand why we have lines 1, 2, and 4 in the header file? What are the purposes of these 4 lines? 3 lines, sorry.
To prevent duplicate inclusion of this. structure or whatever we put in.
That is correct. Okay, so this is a mechanism where it will avoid not duplicate inclusion. It will still be included, but it won't go through the content of the header file if it is already included once. It has to do with the macro definition. So coord_h is a macro, and if ndef is the same thing as if not defined. Okay, if this macro is not defined, then it will go ahead and define and go all the way through #if that is matching this #if. Okay. On the other hand, if coord_h is for whatever reason already defined, then the condition will become false, and it will just skip all the way to #if and not to pass anything in between through to the C compiler. This is a C preprocessor feature, CPP feature, that is actually very handy. If you open up any actual .h file, you will find a mechanism like that, just so that a structure is not redefined over and over again. So what I'll do here is I'm just going to define the structure. So I will say struct coord, and in this case, I'm still thinking about how not to make this the same as your homework assignment, which is kind of difficult. Yeah. Okay, we have X, Y, Z here. And we'll start with a particular subroutine. Okay, so we'll start with a subroutine that does this. So struct coord 0. Okay. So what this subroutine is going to do, coord 0, is to return a structure that is a coordinate that is representing 0, 0, 0. Okay, that's all it's going to do. It will initialize and return the structure. Okay. So we'll focus on just one subroutine, for the time being, because this one will have to. Yep, go ahead.
You have to include the struct part in the prototype.
Say again?
Do you have to include struct in the prototype?
Yes, you do.
Okay.
If you're doing in C++, you do not, but since this is regular C, you have to use the word struct, unless you use type def to get rid of it.
Oh.
Yep. That's one minor but really irritating difference between C and C++. So that makes people who usually program in C++, when they transition in just plain C programming, go like, why is the compiler complaining? Well, because you need the word struct. Okay, so what I'll do is I'm going to split the screen just so that we can keep an eye on the structure itself while we implement the function. So in the bottom screen, I'm going to implement the subroutine. Okay. First thing first, we have to do a #include of the header file. So we're going to #include coord.h. Does everybody understand why we have the concept of a header file in C and C++?
Yeah.
Okay, so that's good? Okay. All right, so by #including coord.h, the .c file will understand the structure definition as well as the prototype of the subroutine. So this way, if I have any type of mistake here, for instance, if I do something like this, instead of returning a structure, instead of return a pointer to a structure, the compiler will choke and say, hey, that's not consistent. Okay, because I have already said that coord will return a structure, not to return a pointer to a structure. The error message will not be the same if this is a C++ program. Because of what feature in C++?
Overloading?
Because of overloading, exactly. So in C++, you can have the same name, the same function name, and yet they take on different parameters or even have different return types. And the C++ compiler will say, it's okay, because line 9 is simply saying that there might be a subroutine that will return an entire structure, but here we are defining a subroutine that returns a pointer to a structure. And they can coexist in C++, but not in C. Okay, in C there's no such thing as overloading, and as a result, if there's a subroutine called coord 0, it must match the return type and the parameters.
Wouldn't
Yep.
C++ still throw an error for not being defined?
No, it will not throw an error when you are compiling coord.cpp in that case, because you don't have to have a prototype to define the subroutine. It's only when it is used then we have a problem. Then if main is making use of coord 0 that returns an entire structure, but the only thing that is defined is the one that returns a pointer, then the linker is going to complain and say, hey, nobody defined that one that is actually being called. It's okay to define an extra one, but it's not being used. Okay. All right. So let's go ahead and take a look at how this one is done, and I have to fix this one so that it doesn't return a pointer. So we'll basically say struct coord x, which is a local variable, and we'll say x dot x is 0. We'll say x dot y is 0, x dot z is 0, and return x as a value. Okay. Most people do not even know that you can return an entire structure in C and C++, and the answer is yes, you can actually do it. Okay, which is a handy feature at times, okay, but it's a very costly feature, as we will see later on. Why this is considered a pretty costly feature. Okay. Are there any questions at this point about this whole thing? Yep.
Is passing a structure by reference also costly?
If you're passing by pointer, it is not costly, because in that case you're only passing a pointer, which are 4 bytes with a 32-bit architecture and 8 bytes with a 64-bit architecture. It is not costly, but it is costly in some other way, because now you are responsible to manage, to initialize and manage the pointers, which can turn out to be even more costly in terms of the development time. Okay. All right, so we have coord.c, coord.h, and we are now going to edit main.c that makes use of it. Okay, so save it first, main.c, and main I'm going to do some printing, so I'm going to pound include stdio. I will also include the header file called coord.h, and then we'll do a main subroutine. And the only way we can make use of this one so far is to create my local variable in main that is a coordinate. And we'll call this one, x also, and we'll say x equals to coord 0, and then we'll use a printf and say, okay, show me the coordinates of this particular structure. So we have x dot x, x dot y, x dot z, and that's the entire program. So this is the entire program written in C, and then later on we'll figure out how to do this in assembly code. Okay. So are there any questions about this? What do you think this program should do? What is the observable output of this program? It will print 3 zeros, okay? Not exactly exciting, okay? But it's a starting point of what we're going to do. Okay, so now would be a good time to use a makefile, because I have multiple source files. It's a good time to make use of a makefile. And I'm just going to borrow the makefile from complex and just edit it a little bit to fit my need. So instead of complex.c, we have coord.c. I don't have a test for this one. I do have a main.c. Is that okay so far? This is why I like the way I set up this particular makefile, is you just have to change the components in terms of source files. It will automatically take care of the header files. Okay, so that's why it's kind of cool, because you don't have to worry about, oh, what if this include file is including the other include file and so on. It will automatically figure out all that stuff. Make it, and just run it. And it prints 3 zeros. Not really exciting in any particular way, but the question now is, how do we implement this in assembly? Is that okay so far? Okay. The first thing is, how do you think a structure looks like in memory? Well, we can do that in GDB. So we'll go ahead and use GDB as an X-ray machine so that we can actually go into the program and say, okay, but how is everything arranged? It's really kind of intuitive. You would not be surprised at all.
Contiguous?
Yeah, contiguous, and they're just off. They are just arranged the same way you define the members in the same order. So X, Y, Z will be in that particular order with nothing in between. Okay, so X will be right next to Y, Y is right next to Z. Okay. But just so that we can observe that, we'll run the program, and what we'll do is we'll print X. Not surprising, okay? This is not really what I'm looking for. What I'm really looking for is the address of X. This is not the address of the first member of X. This is the address of the entire structure X, which just so happens to be the address of the first member of the entire structure. Okay? But because it just kind of makes sense, right? Okay, so that means if I look at the address of the first member of X, which is x.x, hey, it's the same place. Okay, what about Y? Y should be right next to it, 6.8, and Z should be 6C because it's 4 bytes after that. Okay, is that exciting so far? It's not supposed to be. It's not supposed to be because this is kind of what you would expect, right? So when you look at a structure in a high-level programming language, all it really is doing is bundling things together. Okay, so all the members are pretty much right next to each other, but there is no guarantee that they are really right next to each other. Okay, it has to do with packing. In other words, if you declare a member that is an array of, say, 3 characters, okay, the compiler most likely would skip the 4th character, so everything will still be aligned by 4 bytes.
Oh, okay.
Why do you think aligning by 4 bytes is useful? Why are we wasting that 1 byte so everything will still be aligned?
It's a power of 2.
It's a power of 2, but it also has to do with the width of your memory bus. Okay, because if something is off by 1 byte, then it will take 2 memory access instead of 1. So by aligning everything at the 4 byte boundary, it improves the efficiency of your memory bus or memory operations. Okay, so there's no guarantee. Okay, it just turns out to be this way. Okay, all right. So that's good. Yep.
YX has like a greatest address.
So say again.
YX has a largest address.
YX has
A larger. Well, like why it came before the other element. X doesn't have a larger one.
X has the lowest address. It has a 6.4 instead of 6.8 and 6C.
Look at the last digit.
Z.
Yeah.
Okay, and I'm not really sure whether this will work or not, but there's a size of operator in C and C++. So we'll take a look at the size of. It is 12 bytes. Is that part surprising to you that a struct coord is using 12 bytes? It has 3 components, 3 members. Each one is using exactly 4 bytes. And 4 byte is already aligned the way that the processor likes. So there's no need to kind of do any type of tricky stuff to realign things. Okay? All right. So if I were to change the definition of the structure, instead of defining X, Y, Z in that particular order, if I change it to Z, Y, X, then the addresses will be reversed. Okay? Because the compiler is just going by the order of the definition of the member, just because that's the most convenient way to allocate memory in a structure. Okay. All right, so the next thing we will do is to say, well, can we make a small executable so that we can print out all of this stuff here? Okay, instead of using GDB to figure this out, can we do this with a particular program? It would be pretty easy to do, right? So what we'll do is I won't give it a specific name for the time being, so I'm just going to call it, we'll call it gen.c. Okay. So what this program is going to do is to do something that seems to be pretty useless. And what it's going to do is pretty, seems to be pretty useless. So what we'll do is we'll just go ahead and print the size of a struct coord, and I'll just go ahead and declare a particular local variable that is a coord here, and I will print out another %d here, and you guys can tell me what this is actually going to print. Okay, So I'm gonna say void. Char probably will work. I don't think void is gonna work here. If I cast it to a void, maybe this will work too. Not sure whether it will work, but we'll give it a try. Well, I will let the compiler go through it first, just to be sure that this will compile. Okay. So let me compile it first, just to be sure. So that's -c gen.c. Any complaints about it? Oh, that's just a syntax error for getting a semicolon before the one too many parentheses, maybe.
There's one extra.
Yeah.
That very last one that they're pointing at.
Cohort, undeclared, lowercase. Oh, should have used X, right? There we go. And just to check the parentheses, yep, got one too many. That's it. Okay. Wait. Too late. Okay, now that we know that this program compiles, what do you think it's going to print?
It's going to print 12
And?
then 0 minus 0 goes 0.
Well, not 0 minus 0. It is the same address, and that's why it's 0. Okay? I'm casting the address of a member of a structure to an integer. I'm casting the address of the entire structure into an integer, and I'm just subtracting those two integers.
Oh, and since that's the first element, and the entire thing is the same address.
Exactly. Okay. Yep.
Just to clarify, if it accessed the y member,
So it'll be 4.
it'll be 4. Okay.
Yep. Well, we can definitely throw that code in here. Okay. In fact, we'll throw in all three, right? You know, x, y, z, x, y, z, just like that. Is that okay? Right. So we'll go ahead and just I'm gonna shortcut this just to because it doesn't there are no other source files to compile to make this run, so I'm just gonna shortcut it. Okay. And it's complaining. Oh yeah.
Oh,
well,
that's it. Z and that one's good.
I changed the ones that I'm not supposed to.
Yeah.
There we go. There we go. And the output should be 12, 0, 4, and 8.
Yeah.
Okay? So, not really surprising. Okay, now the next question is, can I make this program, just gen.c, can I make it, change something in Makefile so that this program will be sensitive, or at least it will recompile when I change the definition in cohort.h. That shouldn't be too hard, right? I mean, it is just a dependency kind of thing, right? So we'll go ahead and just do that part in Makefile. So even though at this point this program does not seem to be very useful, we're gonna do it. So we'll say gen is gen, that's the name of the executable, and then we'll say gen source is gen.c, okay? And now we have to specify this particular dependency. So $gen depends on $gen source, and .c equals .o, which means the executable depends on the object file of the same name. Is that okay? It's just a trick, it's one of the many things you can do in a Makefile. You can refer to a variable, and then you can say, well, if a file ends with a .c, I want it to end with a .o in this particular case. So all I'm really saying is gen as an executable depends on gen.o, which is perfectly normal, right? The executable depends on the object file. Yep.
Why don't we just put gen.c to cisp310, which is after main.c?
Say again?
Why don't we just put gen.c to the top with cisp310? Why do we need to
Why do we need?
put the gen to gen source?
We want to make another exe.
Because gen is an executable.
One separate.
and I like to put everything into the definition of variables so that we don't need to, change the actual code in the make file in case I want to change the name of the executable. There are other things I have to make changes to, like clean now has more to clean up because now I have to say, oh, gen is something that is actually generated. So when I want to clean up, I also have to clean that up. I have to say gen source, okay, whatever is ending with .c, the .o version should be cleaned up as well when I'm cleaning up everything, okay? So just, basically extension of what we already have in the original code. And the include is also going to change. So we're going to say gen source .c equals .d, which basically means, I need to generate the corresponding dependency file also based on the gen.c file. Because gen.c is not a part of C source. It is on its own, okay? It's separate, but it is separate for a reason, okay? Because it is for a different executable. So let's go check it out and see whether this works or not, okay? Because the first thing we need to do is to fix the source file, make file so that this works. So make clean, and it does, clean up, gen and gen.o, which is good. And we can say make gen, and it does, create the gen file, which is not really a big deal, right? All we did was to extend the make file to also take care of this one extra executable. Is that okay? Okay, now we want to test. If I change anything in coord.h, will it automatically remake gen accordingly? Okay, what do you think? It should, right? Okay. In fact, what you can do also is to go to look at gen.d, which is the dependency file. It says right here, gen.o depends on gen.c and coord.h. So when I update coord.h, gen should be automatically regenerated. So I'll just go ahead and go to coord.h, and as I said a little bit earlier, change the ordering, like so. Now remember, gen.c is still printing in x, y, and z, so the numbers will now be different, right? So we print 12, which is the size of the entire structure, and then it will print 8, and then 4, and then a 0, because it's printing z last. But z in this case is the first member of the entire structure, and so quote unquote naturally, it is the same address of the structure itself. So are we still doing okay so far with all the stuff here? Okay. So we'll go ahead and say make gen, and it does it automatically. /gen just to run the program again, and as expected, it is updating the offsets correctly. Are we still doing okay so far with this stuff? Good once, good twice. You guys are okay with this? Okay. Now we're going to do something with gen.c that is a little bit different from what we have done so far, with C code. What we'll do is we're going to do something like this. We'll say coord_size equals to this, and then we'll say coord_x equals to that, and then there are much better ways to do this if you're really good with macros, but I'm not really that good with the C preprocessor macros, so I'm just going to do it kind of a longish way, because you can see that there's definitely a pattern to this whole thing, right? Whatever member I'm dealing with, I would name coord underscore using that member name, but I'm also going to refer to the address of that member in the expression that I'm actually printing. So if you're really good at macros, you should probably write a macro so there won't be any inconsistency between the name that is printed as opposed to the address of the member that you're printing. Okay? But we're not too concerned with that because we only have 3 items here. Okay. Make gen again, because this time I updated the source code file. And what happens when I do a /gen? Well, that's going to be pretty easy. It's the same numbers that was printed before, but this time there will be like blah, blah, blah equals to that number, right? So we take a look at this. And what does that look like to you? Remember in previous classes, we have seen something like this already in assembly source code. What does that look like to you?
Stack.
Well, this one is not related to the stack, but which assembler feature is it related to? What am I defining? Labels. Yep, I'm defining labels. Or at least this code would be okay to an assembler. An assembler can take this code and say, yep, okay, you just want to define these labels. Okay, the first one is, the label is coord underscore size, and we're just basically saying, every time you refer to the symbol coord underscore size, it is the same thing as seeing 12. Okay, every time you see coord underscore x, it is the same as seeing 8, and so on. But these numbers are now sensitive to the definition in coord.h, which is written in C. You had a question?
No.
Yep. Okay. Great. So now the next question is, what if I were to do this something like this? What did I just do?
Put the output in the core.pin.
Yep, because I just sent the standard output of gen to a file that we call coord.inc. Okay. So when you look at, yep, go ahead.
So what's the .inc instruction?
Hmm?
So what's the .inc extension?
Include, which is going to give you, that's a big clue of how it is going to be used, right?
Yeah.
So when you look at coord.inc, obviously it is not surprising that we just got the same 4 lines, back, right? Is that okay so far? So now I want to integrate this into the makefile also. So I go to makefile and I say, you know what? I want the include file to be named coord.inc. Is that okay? And then I have to specify, but how do we make the include file? Okay, this is one of the ingredients, but how do we make it? So we will need one extra entry to do this. So these are the things that you have to do as well when you do your homework assignment. Okay, what is the dependency? What do you think include inc, coord.inc depends on, based on what I did on the command line? Gen, right? Okay, gen the executable. Okay, fine. We can just name that, right? So we can say, oh, okay, this depends on the executable called gen. Not unreasonable at all, okay? Because after all, on the command line, this is what I did to generate the include file. With any type of makefile rule, you are specifying the target, which is what you want, okay? You're specifying the dependency, which is what ingredients do you need to start off with, and then optionally you can specify the actual command to do it. Now with the other ones, I don't need the actual command because it is quote unquote understood. If you have a whole bunch of .o files and you want an executable, it knows, oh, we just need to do the linking, okay? But in this case, there are no hidden rules that can do this, so I have to spell it out. So I have to spell out and say, gen is the name of the executable, and I believe I have to do a / here, because otherwise it doesn't know where to find it. And then we just specify, that will do it. In other words, instead of referring to the specific names like /gen and coord.inc, I'm relying on the variables to give me the actual names, just to give it one additional layer of abstraction. Are we still doing okay so far? Well, let's test this to see whether it works or not. Okay, so we go back to the command line. Oh, forgot one thing, because when I clean, I need to clean that up too. So we'll just have to make sure that when we clean up, we also specify, this needs to be cleaned up. Is that okay? Now, sorry, go ahead.
You have it in
We have it earlier.
Huh?
You have
Oh,
it.
I had it already? Oh, okay. Then I'll go ahead and, okay, we'll just leave it like this. So we'll say make clean, make coord.inc, and guess what? It automatically figures out how to do that. Great. How is this going to help us implement coord 0? All right, so what we'll do now is we'll take a look at coord.c on one side, and we'll take a look at the assembly implementation coord.uppercase s, well, actually coord0.uppercase s on the other side. Yep, go ahead.
Will this keep track of the parameters on the stack? Will the dot include file help us keep track of parameters on the stack?
Not parameters, but it will help us keep track of the offset of each member of a structure, which is what we need in order to access the individual members of a structure. So that's what we are dealing with here. Okay, so I think some of you are starting to see the connection here, and I think you're also connecting this to your homework assignment because you're basically doing about the same thing. Okay, so on the left-hand side is the C code. On the right-hand side is what I'll do for the assembly code. Okay, so we'll do a pound include coord.inc. Really, can we do this? Absolutely. This is why we changed from lowercase s to uppercase s. Uppercase s convinces GCC that we have to go through the C preprocessor. So the C preprocessor doesn't really care whether the actual programming language is C, C++, or assembly code. It just do all the pound lines, independently, and then it will do the substitutions and whatnot. But it doesn't really do any compiling or assembling or whatever. In fact, if you want to, you can write a plain text file and actually use it to go through CPP to do all the macro processing. It will even do that. Okay. So in this case, pound include is not a problem, even in assembly source code. So this will bring in the definitions of coord size, coord x, coord y, and coord z. Are we still doing okay so far with this code? Okay. And as usual, we have to export the name of the subroutine. In this case, it's coord 0. And then we'll define coord 0 here. Okay. It is a regular subroutine, so it's going to, well, it is kind of a regular subroutine. So we'll start with the usual stuff that we still have to do here. Save EBP, initialize EBP to become my frame pointer, and then do the exact opposite when we are ready to go exit the program. Like so. In other words, lines 5, 6, and 9, 10, they are basically typical entry and exit code of just about any C subroutine. The only exception to this rule would be ISRs or interrupt surface routines and other really kind of tricky type of stuff that you might encounter in professional C programming. But in this class, this is really just typical stuff. When you look at the C code, do we have any parameters? We don't have any parameters. Do we have any local variables? We have one, right? So what I'll do is I'm going to do the same thing here. OEBP is 0. Return address is OEBP plus 4. And we don't have any parameters, or so we think, but we do have a local variable x. So what do you think is going to be the definition of the displacement from where EBP points to the first byte of the structure x? Well, what if I want to use symbolic names? OEBP minus coord size. Okay? Now that's the beauty of being able to use the include file, is when I change that structure, this will change automatically. I don't have to worry, oh, the C code is changed, so now I have to go back into the assembly code and tweak everything by hand. I don't have to do it. This is automatic. Okay? All right, so the next thing we need to do is to think about, okay, let's see how we can do this. Okay? We are going to initialize the 3 members of x to 0. X, y, and z, they all need to be initialized to 0. There's a really quick way to do this, which I'm not going to do. So I will do it the kind of slower way to mirror the C code. Okay?
You mean by just using fill?
Mem set.
Oh, mem set. Can you use fill at a particular location?
Hmm?
Like, so since we know that struct that those members are contiguous, can we just use fill for 12 bytes?
No, fill does not work in this case because fill is a assembler directive. And remember, a directive means it is instruction to the assembler itself, which does not generate any actual runtime code. So it's not going to be helpful to us in this case. But the concept is the same. Okay, we just want to fill those things with zeros. But we have to use move long instructions to do that. Okay. All right. So the most important part is, what does the stack look like at this point? Okay. We have the return address. We saved the EBP, right? And then we allocated a chunk of memory for local variable x, which is a structure. Is that making any sense? Where is x.x? Lowest address, right? Where's x? Well, actually, I redefined the structure, so it's actually the other way around.
We put it the x is first.
Is that making any sense? But we cannot refer to a dot notation in assembly language. That is strictly a C syntax. But given what we have already, how do I get a zero, put a zero into, say, here?
You just need we can move 0 to that memory location.
Right, but how do we specify that location?
It's in
Well, let's think about it step by step. EBP is pointing here, right? And if I use X EBP, it's going to be here. Because X is a negative number. It's negative 12 to be exact. So, X, open paren, percent EBP, close paren, is going to be referring to the lowest part of the entire thing. Yep.
Why x is 12, not 4?
Because the way we define it.
X, 4 plus 4.
Well, the question is, how do we get to x dot x? Okay. Well, once we get to here, what do we need to add to it? What is the displacement of member x from the beginning of a structure coord, right? And it has a particular name. It's not 0. It is. We have to avoid using the actual numbers. We have to remember the symbolic name of those offsets, because otherwise your code will break when I change the .x file. So it is coord. Well, I have to destroy these pins. Coord underscore x. Is that making any sense? So that means the actual assembly code is going to be x plus, well, since addition is commutative, I don't really need to know, specify in one order or the other. But this makes more sense because it is somewhat resembling the C code, because we refer to the variable first and then we refer to the member offset. And then the whole thing is the displacement in the base operand. Are we sufficiently convinced that on line 11 this is going to do the trick? Yep.
But we didn't define that code underscore x anywhere.
In coord.inc, that's the whole exercise that we did a little bit earlier, with gen, the executable.
Yes.
That will spill out the definition that we need to put into this particular program. Well, the other two would be pretty easy, right? Like that. Y, Z. All right. Well, so the C code as far as lines 7, 8, and 9 are concerned are done. Cool. Now here comes the most mysterious part. How do we return it? Does it fit into EAX? No. Well, is it a scalar? Is it considered a scalar type?
Again, scale.
It's not a scalar type. A structure is not a scalar. Even if a structure only has one scalar as a member, it is still not a scalar. It's not considered a scalar. Yep.
Could you return x, the address of x, for the
You are getting you're getting to the mechanism to actually do it. So what we'll do is we'll take a pause from the actual code and then we'll read some documentation. Okay. Whenever we feel kind of stumped, and know, I don't really know how to do this, it's time to read the manual. The fine manual.
Well, yeah, the RFM.
This one actually belongs to the previous section. So we'll go back to the whole class first, and then we'll go to the previous section. So we'll go back to subroutines, and we'll go ahead and read C calling convention. Okay. How many people did not follow this link because I have said, why write it when it's already written? And then people think, why read it when it's already written? This is actually important stuff, okay? It is actually important stuff. All right, so when we're here, we'll just go ahead and look for struct space. Oh, not that. It's actually somewhere down the list. Okay, there we go. This is actually the way that the GCC does it, which is the de facto standard of almost all C compilers. So we'll just go ahead and read this sentence here. 2 sentences. When returning struct/class, the calling code, the caller, is going to allocate the space and pass a pointer to the space via a hidden parameter on the stack. That is actually turned out to be the quote-unquote hidden first parameter. The call function will write the return value to this address. So what that means is the picture of the stack is actually incomplete at this point because there's actually a hidden pointer here. I would call this the return value pointer. Okay, it's only using up 4 bytes. Okay, the caller is setting this up, so the caller would actually push this last on the stack, and this is a pointer pointing to a space that the caller has allocated to store the return value of the subroutine. Okay, now where exactly is this place? Is it on the stack? Is it in the heap? Is it somewhere else? I don't know. The caller knows. I don't know. Okay, so at this point, because I'm the subroutine that is being called, I'm not too concerned about where it is. I just know that I have a pointer to that place. Are we doing okay so far? Is that okay? All right. So now that we understand this particular standard, what we are lacking here is one thing that we have not defined. We have already the return address. Now we'll say the return value pointer is return address plus 4. I like symbolic names. I don't really want to refer to numbers, direct numbers, displacements. So this time, what I need to do is, if I want to follow the C code, I'm going to have to copy the entire structure X to wherever this pointer is, okay? Which is a hassle depending on the size of the array, of the structure. So what you might want to do is to defer all the copying to a subroutine that is specializing in copying, okay? Does anyone want to name that particular subroutine? In C strings, you have string copy. So this is not string copy because it's null terminated.
So struct copy, spelled the same way, STR.
Okay. Well, there's CPY somewhere, okay? At least there's one thing for certain. When something is misspelled, it is consistent, right? Okay, so we'll still do a mem copy, okay? Memory copy. So mem copy, when you do this from assembly language, there's no need to pound include the header file because nobody is going to check whether we pass parameters correctly or not. So what we'll do is we'll just go ahead and call mem copy to copy a chunk of memory to another place. Why implement your own loop to copy byte by byte when you can just call someone else to do it, right? Okay, so how many parameters are we dealing with? We have 3 parameters. The last one, since we have to push it first, is the number of bytes to push, number of bytes to copy. That is just a regular integer. Size underscore t, at least with a 32-bit architecture, is a 32-bit integer, 4 bytes. Source is where we are copying from, and you can definitely tell if it's not the name, you can tell from the const of the void pointer because it clearly states that we're not supposed to change whatever is pointed by src source. And the destination is the first parameter, which is pushed last. Okay, so we have number of bytes, source, and destination to push on the stack. Now we'll go back to the assembly code and say, okay, how do we do this? We know one thing for sure. We can say, this part is for sure, right? And because I have this habit of cleaning up the stack afterwards, this part is for sure as well. Okay, so we are going to readjust the stack because we would have taken up 4 bytes to store all the parameters. Okay, now what are we pushing? We have push, push, and push because we got 3 32-bit things to pass. The first one to push is the last parameter, which is the number of bytes that we are copying. How many bytes are we copying?
Size of
Chord underscore
size.
size. Very good. So this is a immediate operand chord underscore size. If you don't like using cisp instructions like this one, you can always just move $chord size into EAX and then push EAX. That will work as well. I'm just going to use a shorthand here. What is the next one? The source, right? Where we are copying from. And that's a difficult one because that's our X. So, and we are not pushing X itself on the stack. We're pushing the address of X on the stack. Okay, so how do we push the address of X, which is a local variable, on the stack? How would you calculate the address of X if you have to do it by hand? Okay, just look at the picture. We still have the picture here. This is EBP. We know where EBP is.
Yeah.
And X is down here. So if I copy EBP to some place and just add X as a symbol to it, that should get me the address of local variable X. Is that making any sense? Okay. So what we can do, there are several ways to do it. I'm just going to do it the trickier way. Is we push the register EBP first, and then we'll do the calculation on the stack, which is just doing a add $X to whatever we just pushed on the stack. Whoops. ESP. There we go. Is that okay so far? I push the register EBP on the stack. Okay, so now we have a copy of EBP on the stack, which is the frame pointer, right? But what we want is not the frame pointer. We want the address of X. We know where the address is. It is X bytes from EBP, or from where EBP points to. So I'm just doing all the arithmetics on the stack instead of using another register to do the calculation. Is that okay? Kind of? Okay. The last push is the destination. Where am I supposed to copy all of this stuff to? Oh, that pointer over here, right? Am I copying to the address of the pointer? Or am I copying to where the pointer points to? Where the pointer points to, right? Yep, go ahead.
Why do we add X to ESP like EBP?
Because I just pushed EBP on the stack and we need to calculate what is EBP plus X.
So what's the value in
EBP, ESP or EBP?
ESP.
ESP points to the last thing that we just pushed on the stack, which in this case is the frame pointer. Okay, last thing we're pushing on the stack is the pointer itself, which we named the return value pointer. That would do it. In other words, we are pushing the pointer itself on the stack. We're not going to push the address of the pointer to the stack. We're just pushing the pointer because that's already telling us where we are supposed to copy all this stuff to, right? Are we doing okay so far with this code from line 9 all the way up to line 20? The rest is just cleaning up and no big deal. Yep.
Do you need to add 12 to the stack pointer before you move 0 before you change some stuff?
Good point. Yep, you're absolutely right. I forgot to allocate the actual space for our local variable. Thank you so much. So we are adding X to ESP. Thank you. Good catch. And if you don't do that, it will end up doing, well, what is it going to do if you forget to do something like this to allocate for your local variable, but the rest of the code is actually correct? What is it going to do? You'll just be messing around stuff on the stack where you're not supposed to. And the symptom won't show up until you actually use the stack for anything. Because the way we address the local variable x is relative to the frame pointer. In other words, we are using a part of the stack that is not allocated yet, as if it is allocated. So nothing is going to happen until we use a push instruction or call instruction, where it will actually overwrite the stuff that we thought was saved from being overwritten. So, and the call itself is not going to be a problem. It's only when it comes back, what was originally supposed to be there is not there anymore. In this case, it's even worse because what would happen is the structure will be quote unquote initialized correctly because those 3 zeros will be there by the time we get to line 17. But the very process of setting up the stack to copy those bytes to the final destination, copyrighted by Sony, but by that process, it's going to corrupt the very same content that we are supposed to copy. So the structure that would end up being returned would end up being the parameters to Mem Copy, which will look kind of funky because you will end up with a 12 as x, and then some really gibberish stuff because they correspond to addresses on the stack as x and y, as y and z, sorry. Okay. Yep.
On a place of add, can we do a base pointer addressing instead of $x?
Can we use?
Base pointer addressing?
No. You cannot because we are basically subtracting 12 from the stack pointer.
So if we do like a base pointer addressing, then we don't have to reset in the end.
Well, we are resetting it in the end because by the time we get to line 24, it's going to restore the stack pointer.
Then we don't have to subtract like a $x from ESP.
You mean over here?
Yes.
It's not necessary. You can do it, it doesn't hurt anything, but you don't need to do it. So that instruction, line 24, if you put it there, great, but you don't really need it because line 25 is going to do it anyway. Because line 25 is going to restore the stack pointer back to wherever EBP points to. And therefore, anything that you allocate below that point is automatically cleaned up. It doesn't even care how much stuff you have allocated because you're just physically moving the stack pointer back to the frame pointer, and so everything is cleaned up at that point. And that's why line 24 is not needed. If you put it there, it's not going to hurt, but it's not needed. Okay. Are there any questions about this particular subroutine? Do you think it's going to work? Maybe. Well, no. We never take tax word for anything.
No, we don't. Okay, but what I do want to know is that we're just for your own like those jollies. Did we use the whole include file? We could have defined those labels, chord X and chord Y, inside of this file itself.
We could have, but that would not make it sensitive to the definition in chord.h.
Oh, because of all those dependencies that we established.
Yep. This is the mechanism to make sure that your assembly code that is making use of a structure that is defined in C would adjust accordingly when the definition in C has changed.
By the fact that we kind of printed it out and then
Right. By the gen program. Yeah, the gen program is the link that goes between the C code and the assembly code. All right, so we'll give it a try and see if it works. Okay, but before we can do that, we'll have to make some adjustments to the makefile and also the source file. So we'll now have to specify coord 0.uppercase s is here, and we'll I just made some changes. I'm not supposed to. Main.c. Nope, that one does not need to be changed. It's coord.c that needs to be changed. And what we need to do is to just comment out this code here. This is one way to do commenting out instead of using the /* and the */, which is not really the best way because that way of commenting out cannot be nested. This can be nested.
Well, isn't that true? Wait, that's false.
Yeah, it is false. So if the condition is false after the pound if, it will skip everything until it hits the matching end if. So this is why this is a quick and easy way to comment out a block of code where the block of code itself may contain slash star and star slash as comments. If you use slash star and star slash, it cannot be nested. This way it can be nested. Most editors that have syntax highlighting would actually recognize pound if 0 as a special construct. So when you say pound if 0 and then a pound and if, the block in between will be grayed out using syntax highlighting. Most syntax highlighters would actually recognize it. It's a pretty well-known trick amongst C programmers. And I think VI knows that too. Let me give it a try. Yep. See how it's all kind of turned into dark blue? Yeah, it is. Okay, fine. But syntax highlighting is great because you can actually visually see, oh, okay, that code is now not going to be a part of the program.
And if you really wanted to, you could change that.
Yeah, exactly. All right, so I think we have made all the preparations. We'll just say make. Wow, the whole thing just made. And it works, okay? Well, but somebody can complain and say, well, but they're all zeros. How do we know that it is putting the right value into the right place, right? So let's go ahead and change the code so x is going to be it's 1, 10, and 100, okay? So x is 1, y is 10, and z is 100, okay? So you go back into the source code, which is coord 0.uppercase s, and then we change x, the value of x to be 1, the next one is 10, and the next one to 100 accordingly, okay? Is that okay? I think that's consistent with what I just said, right? And then we'll do something even more funky just to see if we can trip up this particular program. So we'll say int x is here, and then we'll define some kind of char array here. We'll make it some really odd number, like 13. And then we'll have y, and then we'll have z here. And then we'll have some more funky stuff here. Make it, I don't know. What do you guys feel like? 23? Huh? 29. How about another prime number? Okay. Okay. So we're basically messing up the structure by changing the order of the members and inserting stuff in between that absolutely has nothing to do with the particular program that we're dealing with. And we want to see if the program or the makefile, the dependencies, will figure this out and say, uh-oh, we need to redo this and that. Yep.
You're missing a Y.
I'm missing a Y. You are absolutely correct. In all the excitement of messing up this program, I forgot. Okay, there we go.
2 semicolons.
2 semicolons are missing. You guys will make excellent compilers. All right, very good. Okay, so we'll see whether this will trip up the program or not, because this is certainly a lot of stuff, right? Changing the order, putting stuff in between, and all that stuff. So we'll say make, and okay, if you just look at the ordering of the compiling and all the commands here, let's see if that makes sense, okay? That's the first thing we want to do. GCC core 0-s-mm is basically saying we are regenerating the dependency file, okay? Because we have done some changes to the source file itself. It is recompiling core.c in the C version, even though now it has no function definition. But the makefile does not understand actual C definition, so it will say, okay, you're still depending on core.h. Let's go ahead and recompile. That makes sense. It's recompiling gen.c because that also includes core.h. So every time you do any changes to core.h, it will recompile gen.c to become gen.o, the new object file. It's linking gen.o to gen, okay, to create the executable that we rely on to create or recreate, in this case, the include file, which it did. Okay, so then it ran /gen to regenerate the include file, and then after that, it recompile, or reassemble, I should say, cohort 0.s. Because the include file is now updated, it's time to reassemble the assembly file, the assembly source file. Once it is done, now we can take cohort.o, cohort 0.o, and main.o to relink everything into main as the executable. So the ordering seems to make sense, okay? It seems to be doing everything in the right order. So the moment of truth is this going to print 1, 10, and 100? Because those are the three members, or the values of the three members of the structure, and it does. Are we doing okay so far with this?
Okay, but so if we were to go back in GDB right now, the size of X would no longer be 12.
The size of X will no longer be 12. You are correct. And do you really care about how much it is?
I thought that the last time we were using the fact that they were contiguous, that they were next to each other, so we were to
Right.
find
Correct. Okay,
why
so
we
you
just had
want
to
it.
move.
Okay, I understand your question. Or I understand what you are trying to get to. So let's go ahead and put a breakpoint on line, say 9. Okay, run the program, and we'll print X out. Okay, it has a bunch of useless stuff, as the name of the members suggests, right? And we have, so what we'll do is we'll print the address of x.x, okay? And then we'll print useless. And the most important one is going to be z. Okay, so when you look at 3.8 in hexadecimal and 4.8 in hexadecimal, how many bytes are actually between useless, which is supposed to only have 13 bytes, and z? 16 bytes. And did I say something about aligning by 4, something like that? That's basically what it is. Because 13 bytes, the next one up, the next multiple of 4 that is greater than or equal to 13 is 16. That's why it's using up extra memory, because it wants to align everything to 4-byte boundaries. Now, if you're dealing with a particular application where you really do not want to waste any space, instead you're willing to pay penalty in terms of performance, you can actually tell the compiler, there's a flag to tell the compiler and say, do not align by 4 bytes. Instead, you pack everything as tightly as possible. That is an option that is available. All right, so the next thing we want to do is to say, oh, but what is the size of X? Now it's 60. And guess what? 60 is divisible by 4. Are we doing okay so far? How do we pass a structure by value? You quote unquote, you push it on the stack, right? But there's no one single instruction that can push a 60-byte thing on the stack. So instead, what are you going to do? You allocate a space, and then what do? Mem copy. Okay, so every time you want to copy a chunk of bytes where the number of bytes that you have to copy is kind of undetermined, you want to use mem copy. So you set up the number of bytes, push the number of bytes to copy, where you're copying from, and also where you're copying to. So those are the 3 things that you have to pass on the stack when you want to use mem copy. Are there any questions about this? Yep.
When you use mem copy, it copies it to the stack itself.
Okay, well, let's go ahead and write a program to exercise that part. Okay, so we'll go to core.c and we'll implement a new function. And let me see what I'm going to do here. I know. Int is coord is 0, and we'll pass a struct coord to it. So in C, the implementation is going to be like this. All it's going to do is to say return x.x equals to 0, and x.y equal to 0, and x.z equal to 0. Is that okay so far? So I'm just checking whether a particular coordinate, that is my parameter, is all zeros. Okay, that's all I'm going to do here. I am not going to implement this one in assembly. I'm going to implement the caller in assembly, which is the bigger concern, right? As far as the calling is concerned, we know where to find X. We also know how many bytes it's going to take up on the stack. So it's not that much of a big deal. It is still the caller that is going to be the big deal. Okay, so let me see. Since we are kind of running out of time, I'm going to shortcut this one a little bit by putting this one here. Let's say okay, so the test subroutine is now going to be implemented in assembly, and the content of test is going to be like this. So pound if 0, pound and if. I'm just going to give you the code of test in C so that you can see how it is corresponding to assembly. So and then we turn, what was it again? Coord is 0. Pass X as the parameter. Okay, so that's what I'm going to implement in assembly. Are we still doing okay so far with this code? Okay. Split the screen. Oh, okay, wrong way. I don't know how to do the split in vertical, inside Vim. So I'm going to do this. Okay, there we go. All right. So the first thing we do in test is we have to pound include coord.inc, the include file that includes all the definitions related to the structure. And then we have .text, .global, test label, push EBP, move ESP to EBP, add $x to ESP to allocate space on the stack. I'm going to make this code mirror the C code exactly, so that's why I'm going to go through all this process here. There's a shortcut to do this, but I'm not going to take the shortcut. So the end is going to be the reverse of the move instruction, pop L instruction, and the return instruction. And to define all the labels, that's it. Okay, I don't have any parameters. I do have one local variable, which is X. I was looking at the wrong code. There we go. So X is old EBP minus the size of a structure, so that will be coord underscore size. Okay, are we okay so far with the setup of this subroutine? I have not written a single line of code for the subroutine, the content of the subroutine, but I have done everything to structure the whole thing. Is that okay? All right, so let's go ahead and write the subroutine and start with x equals to coord 0. So this time we do have to think about from the perspective of the caller, how are we allocating the space for a structure? Okay, so that we can pass that as a parameter, as a hidden parameter to the subroutine. Okay. Where do you think I should do this allocation? I only need it now. Once I'm done with this particular statement, I don't need that space anymore. So what would be the best way to do it? On the stack. Okay, how do we allocate that many bytes on the stack? How about something like that? Right? In other words, I'm subtracting basically 60 in this case from the stack pointer. Okay, so that just moves the bookmark down by 60 bytes. What I'm really doing is to say, oh, these 60 bytes are now in use. I did not initialize it to anything. I'm just saying it is now in use. Okay, and I will pass that pointer, to the subroutine eventually, which is the next thing I'm going to do. Okay. And what is the address of this thing that I just allocated on the stack? What about the stack pointer itself? The stack pointer is pointing to that space right now, because the whole thing about the stack pointer is it points to the very last thing that we pushed, quote unquote, push on the stack. That is basically a push, but without initializing or changing the content of what we allocate. So that is okay. So this instruction looks kind of circular and looks kind of confusing. So what it's going to do is to push the current value of the stack pointer on the stack, which is exactly what we want. Okay. And then now we can call the subroutine. So we call coord 0, which will initialize, the stack. And when it returns, what we'll do is we'll deallocate those 4 bytes first. The parameter to the subroutine is now deallocated. And then what do? We now have 60 bytes sitting on the stack. That is the return value of coord 0. What am I going to do with that? We want to copy that to our local variable x, right? So, and how do we copy a chunk of bytes where the number of bytes is not really known ahead of time? We just know that the label is defined to that size. Mem copy, right? So we're going to do a mem copy here. So the mem copy needs 3 parameters. We have to first push the number of bytes that we are copying, which is coord size, right? Then we have to push the source address, where we are copying from. Where are we copying from in this case? It's a little bit tricky because it's not a stack pointer anymore. Because I just changed it.
Plus 4.
Okay, so it's the stack pointer. Yep, it's plus 4. But I cannot do something like this. As much as we want to do something like this, basically it's 4 plus the stack pointer. I cannot do it. The syntax does not allow it. The instruction does not allow it. So what I will need to do is to push the stack pointer itself and then do the math afterwards. So adding 4 to whatever the stack pointer points to, which was the stack pointer itself. Okay. So that would make the second parameter. What about the first parameter? That's our destination, where we are copying to. Where exactly are we copying the return value to, according to the C code on line 12? Our local variable x, right? Well, what is the address of our local variable x? Push EBP on the stack first, and then do the calculation on the stack, just like before. Remember the previous program? The previous code that I wrote, had about the same structure. So now that all the parameters are done, we just do a mem copy. And when we come back, we adjust the stack pointer. And that will complete line 12. Are we still doing okay so far? What about line 13? Line 13 has 2 mem copies in it. Because the first thing we have to copy is from x to a parameter on the stack. Then we have to, no, that's it, never mind. Okay, just 1 mem copy because we have to set up for the parameter. All right, so now we're dealing with line 13 on the C code side. There's not much we can do. The first thing we have to do is to push x on the stack. But x is an entire structure. So how do we allocate for the entire structure on the stack? We have done it already. Oh, you know what? I forgot one thing. Forgot one more thing. After we do the mem copy, after the adding 12 to the stack, I still have that return value thing on the stack at this point. Remember, we allocated like 60 bytes on the stack for the return value of coord 0. That is still sitting on the stack, even though it's useless now. Maybe I should deallocate it, right? How do I deallocate it? How many bytes am I supposed to deallocate?
Coord size,
add coord size to the stack pointer. That will deallocate the space that I have allocated for the return value of coord 0. Are we still doing okay so far? You guys look a little tired. All right. So now that we have everything done on line 12, we are now focusing on line 13. We have to push x on the stack. Well, as much as we want to do something like this, we can't, because that is still only going to push the first 4 bytes
of a structure that is using 60 bytes at this time, okay? So it's not gonna work.
Well, for those of you who want to do it, you can say, push x plus 56, push x plus 52, push x plus 48, and so on. But what happens when I change the structure cohort? Your program is going to break. So you don't want to do it, okay? Do not do it that way. So the way to do this is kind of the same thing. It's kind of tedious, but that's the way it works, is to allocate the space first, okay? So we are basically subtracting cohort size again. We just added that to the stack. Now we're subtracting it from the stack again. But the purpose is different, okay? This time it is not the return value of a subroutine. This time it is a parameter to a subroutine. So we're allocating that space, and now we can do the mem copy call. So we push cohort size on the stack because that's the third parameter. And then we push the parameter that is the source, which is my local variable x. So that would make it push EBP add $x to whatever the stack pointer is pointing to. That's the second parameter. That's the second parameter. The first parameter is the destination. Where am I copying this stuff to? Uh-oh, we are now 2 pushes away from the space that I have just allocated for the parameter itself. So how do I get back to it? How do we calculate the address of the parameter that we are pushing on the stack? We are 2 push L's away from that space. ESP plus 8, okay? But we cannot just say push ESP plus 8. We can push ESP first, and then we say add 8 to whatever we just pushed on the stack. That should push all the 3 parameters on the stack. Time to call mem copy. And after mem copy, this time adjusting the stack to deallocate the parameters is of paramount importance, because otherwise these 12 bytes will be considered to be a part of the parameter that you are passing to cohort is 0. That would be wrong. Okay, so that's why this time we absolutely have to deallocate these 12 bytes. Okay. Well, once we deallocate these 12 bytes, then it will only be the 60 bytes, which is a structure on the stack. It is time to call the subroutine that we are actually going to call, which is cohort is 0. When it comes back, EAX has the result already, which is good. We just have to, as a habit, it is good to clean up the stack. To clean up the stack, we have to basically just do a add long cohort size to ESP, because we did the subtraction on line 31 to do the allocation. So the add long is going to be used for the deallocation. I think that should be it, because the value that is returning is already in EAX, because cohort is 0 returns an integer. It does not return an entire structure. So EAX is where it is. So I think this whole thing is done. Except this is going to return false because of the way I implemented cohort is 0. So I have to change it back to all zeros. So save this, go to cohort 0.s, change this one so we go back to what it's supposed to do. Remember, I kind of hacked this one just to make sure the code is working. Okay. I think that should be it. So we'll just feel kind of brave and see if it works or not. GDB main. Put a breakpoint. Oh, I did not call it.
Being able to just compile.
Okay. Sorry?
No, I just saying I'm ready to just compile.
Well, I did not call it. Now that I have it defined, I did not call test. So I'm going to declare y here and say y equals test. There we go. So we'll put a breakpoint on line 24. Okay, it's complaining undefined reference to test. Oh, that's because I did not change the make file to also refer to test.uppercase s. There we go. Okay.
fact, I should be using this more consistently. Put a breakpoint on line 24, run the program, and this is the moment of truth. So how many people think that I should just step over the function because you are kind of eager to go home and have dinner? I can tell from your lack of enthusiasm. To quote Darth Vader, I find your lack of enthusiasm disturbing. That's when he patrolled the Death Star when it was half finished and it was kind of behind schedule a little bit. Okay, so let's see, print y. Y is 1. It is true. It works. Okay, so what I'll do is I'm going to package up this whole thing and post it onto Moodle. So that will give you a point of reference to do everything that you need to do for the homework assignment. Okay? If you're getting the concept right now, the homework assignment is tedious. Okay? There's a lot of setting up to call Mem Copy. If you're not quite understanding the concepts, it might be helpful to read the documents for one thing, watch the video again, and as you're watching the video, think about the homework assignment. Okay, so that's something that you might want to do if you're just kind of like, well, I'm getting the general idea, but I need to know more about the details. Okay. All right, well, that will end today's lecture. I will go to the lab later on. I just need to kind of pack up things a little bit and not load stuff to Moodle right now. Well, actually, I'm going to do that all for the lab. So let's wait. Stop the lecture. And it's good.